This particular slide is going to model the rules that we're going to learn in just a moment for decimal division. So you want to make sure you write this whole slide in your notes, and this is a 10 by 10 grid. So what you want to do is you want to draw a nice big square that takes up not the entire page, but maybe close to half the page. And you want to make sure that it is 10 across and 10 down. And then you'll have the grid that you need to do this, to write this with me. So this problem says that we want to multiply 4/10 by 6/10. So if we count along here, these are tenths because there are, if you look, there are 10 this way and there are 10 this way. So we have tenths. And the first number that we want is 4/10. So we want this, essentially you can think of it as a rectangle, that we're going to draw a rectangle that's 4/10 by 6/10. And so the rectangle is going to be 4/10. So there's 1, 2, 3, 4/10 by 6/10. So 1, 2, 3, 4, 5, 6, 6/10. And then if we color in the rest of this rectangle, this 4/10 by 6/10 rectangle, this lovely little rectangle here, yay, rectangle. Okay, so we have this beautiful rectangle now that is colored in, and it is a 4/10 by 6/10. Well, if we were to count the squares that are in this rectangle, and we can even redraw the lines here, then we would notice that there are 24 squares. However, these are not 24/10 anymore because it's now two-dimensional. Instead, now we have to look at the total number of squares in this grid. And if you look at the total number of squares in this grid, what is a 10 by 10? How many squares are in a 10 by 10 grid? Well, there are 100. So in this entire grid, we have 100 tenths. So really we're looking at hundredths. So there are 24 squares in here, but it's now 24 out of 100, so it's 24 hundredths. So we took one row of 10 and colored in 4/10s. And then we took one row of 10s and we colored in 6 of them. And so we had 4/10 by 6/10. And then we filled in the rest of that rectangle to give us 24 out of the total 100 squares. And that is one of the rules, that demonstrates the rule for where the decimal goes, because you'll notice here that we had tenths and we had tenths, but then we ended up with hundredths. Let's look at another one that deals with more than one decimal place. So not both tenths, but some additional decimal places. So this problem is going to model what happens when we have two different one-dimensional pieces and turned it into a two-dimensional piece. So our first number here is 5/10. Well, this is a 10 by 100 grid, so there's 10 tens, so that's 100. And so I'm going to use 5 of my 10, so 5/10. So 1, 2, 3, 4, 5. And then my second one-dimensional line is 33 out of my 100. So 33 hundredths, I'm going to use 33 out of my 100 this way, because there are 100 this way. So 1, 2, 3. This is 10. Each of these little grids is 10. So that's 10. This one is 20. And this one is 30. And then 1, 2, 3. So now I have 5/10 and 33/100. Now, if I complete this rectangle here, if I then turn it into a two-dimensional figure here, there we go, then I'm looking at this many squares out of the total. Well, if I have a grid that is 10 by 1,000, 10 by 100, so 10 by 100, that's going to be 1,000 squares. So in this entire thing, there are 1,000 squares. Well, if I had 5 here and 33 here, that's 33 by 5, which is 165 squares. So there are 165 squares in here, but it's 165 of my 1,000. It's 165 out of the 1,000 total squares. Well, that means it's 165 thousandths. So I write it as 165 thousandths. So you'll notice that when we do tenths by hundredths, it turns into thousandths. On the previous model, we did tenths times tenths, and it turned into 100. So if you think about what you're doing here is you're really multiplying the powers of 10 for your place values, and that's getting your answer of the power of 10. So if you do tenths times tenths, you're going to end up with hundredths. If you do tenths times hundredths, you're going to end up with thousandths. If you do hundredths times hundredths, you're basically doing 100 times 100, which is going to give you 10,000. So you'll have 10,000. So if you think about it in terms of the place value, that makes it a little easier to remember the rule that is going to come up on the next slide. This is example 1, and it's the example using the steps or the algorithm for multiplying decimals. You want to make sure that you have this whole example in your notes section. And this is not going to use the model, it's going to use, again, the algorithm or the steps. So the first step is to write the longer number first. Well, here we actually have the same number of digits because that 0 in front of the 2400ths is just visually more appealing than having nothing there. But since technically it is longer, I will write that one first. So I have 0 and 2400ths. And then it says to write the second number beneath it, or the other number beneath it, lining up the digits. So I'm going to start from the right. So I have a 7, then I have my decimal, and then I have my 3. You'll notice that the place values are not lined up. Instead, it is the digits, the rightmost digit, and then the next digit, and then the next digit. The multiplication doesn't have to do with total place value. It's not the same thing as addition and subtraction. Instead, it has to do with those powers of 10 going from one dimension to two. So tenths by hundredths is thousandths. So after we line up our problem in our vertical format, we are going to do the next step, which is multiply the numbers normally. So we have 7 times 4 is 28. 7 times 2 is 14, plus our extra 2 is 16. And 7 times 0 is 0, and plus 1 is 1. And then, of course, we have our placeholder here. We know how to multiply, so it's our placeholder. And we have 3 times 4, which is 12. And 3 times 2 is 6, plus 1 is 7. And then 3 times 0 is just 0. And then we add our partial products. So we get 8, 8, 8, and then of course a 0 here. We can just leave the 0 off if you want. And then we have to figure out where the decimal goes. Now, if you think back to the model, we're really doing tenths times hundredths. And tenths times hundredths equals thousandths. But when we apply the algorithm or the rule, we simply want to count how many digits are behind the decimal in the problem. Well, in this number, there's 1, and in this number, there are 2. So there are 3 digits behind the decimal, which means I need to go 1, 2, 3. So there are going to be 3 digits behind the decimal in my answer. So it's going to be 1, 2, 3 digits behind. And if you notice, that is 888 thousandths, which is exactly what it should be, because it should be out of 1,000. Please make sure you ask any questions if there's something you don't understand in this example. This is example 2, and again, you want to write the whole example into your notes section. If you think about the model, we have tenths and we have hundredths. So if you think about tenths times hundredths, it's thousandths. So going in, I know that I'm going to have an answer that has 3 decimal places because it's going to be thousandths. And if I think about that before, I risk running into less problems or risk making fewer errors. You don't have to think about that, but I highly recommend it because, again, it will save you some trouble. Let's follow the algorithm. The algorithm says to write the longer number first. So the longer number here is 5 and 17 hundredths. And then it says to write the other number beneath it, lining up the digits. So I'm going to start from the rightmost number, the digit, which is the 1, and then there's a decimal, and then there's a 3. So again, you'll notice that we are not lining up the place values or the decimal because that makes extra work. Can you do it? Absolutely. It just adds extra steps in because you have to then account for empty place values. So this is a faster way, which is why it's the algorithm, so that you make sure that you are doing it correctly. So then once we have it lined up, we are going to multiply normally. So 7 times 1 is 7, 1 times 1 is 1, 5 times 1 is 5, and then we have our placeholder. 3 times 7 is 21, 3 times 1 is 3, plus 2 is 5, and 3 times 5 is 15. Then I'm going to add my partial products, and I get 7, 2, 10, 6, 1. And then I count how many digits are behind the decimal point in my problem. Well, my first number here, my top number has 2, and my bottom number has 1. So there's 2 here, there's 1 here, which means there's going to be 3 in my problem. So I need to have my 1, 2, 3 numbers behind the decimal. So it's going to be 16, and if you look, it is 27 thousandths. I have my 3 decimal places. So that matches what I know that I should have in my problem if I think about that grid model. Again, if you have any questions about this example, please make sure to ask.